Hello and welcome back. In this video I want to discuss how we can use convolutional neural networks in Keras to TensorFlow and go through the whole code of how we can put everything together to analyze data. Convolutional neural networks play a large role in modern machine learning because they allow us to analyze images. Before we dive into material science applications, we want to use a well-known practice data set called the MNIST data. These data contain a large number of handwritten digits in the range from 0 to 9, i.e. all 10 digits, and our task is on recognizing from a handwritten digit what this digit is. Because this is such a well-known practice data set, there are lots of convenience functions that allow us to download the data, and we can look at an arbitrary example, for example index 1, 2, 3, 4. And this happens to be the number 3, and it's a black and white image, or rather it's presented as a grayscale image. You can see from the anti-aliasing that makes it a bit smoother, and that we have less black boxes and more gray values around, but we only have one color channel. So the first step is to create a shape of the tensor, and tensor means that we have this object that will hold the data when we pass it to the network, and we need to do this explicitly. So we have the length of the training and the test data. We have 28 by 28 pixels. This is here. This is what the size of the images in the dataset are, and we have one color channel, and we use this as float numbers. We also need to normalize this to stick to the convention of how these data are represented. So our first task is to build a very simple model. So we take one convolutional layer. We use the TensorFlow Keras API and use a sequential model. And we have one convolutional layer with a given kernel size and padding and stride. If you haven't used this in a while, it's a good opportunity to remind yourselves about the basics of convolutional neural networks. This essentially means we have a 3 by 3 matrix kernel and take one step in each direction all the time. We also take padding and have an activation function. Our input shape is 28 by 28. This is the size of the image with one color channel. And we add max pooling, and then because it's a simple model, we just have one dense layer here, drop off regularization, and then another dense layer with 10 classes, because we have 10 digits. The activation is then a softmax function because we want to represent each of the classes in the range from 0 to 1, and the highest one is then the class. So for example, if node number 8 exceeds or is the highest, we want to have this for an image that shows figure 8. And this is how the network looks a bit more like compact. You see that we have already quite a number of parameters that we need to train for such a simple model. Now we need to specify how we train the network. So we use an optimizer to take care of the gradient descent. And again, if you haven't used neural networks in a bit, it's a good idea to pause now the video and reacquaint yourself with how neural networks work and how they are trained. So we use the Adam optimizer here with a given learning rate and a loss function because we have a classification. We use the sparse category cross entropy. And as a metric, we look at the accuracy. Now that we have our model defined and compiled, we can use model fit and then record the training progress as we go along. So we do this for 15 epochs now. And then the training will progress, and we can evaluate the final accuracy, and we can also plot the loss function as the number of epochs and the accuracy. And you will see that this goes up very quickly, and this is mainly because for such a simple data set, even this very simple model can handle this very well. You will look at the confusion matrix, right? So the predicted output is on the x-axis and the true output is on the y-axis, and that should be a diagonal line. So each predicted label should be correct and represent the true label. And we can see that even for such a simple model, there are only few instances where the network makes a small mistake. We can see how this looks like if we have a more complex model. So for example, we could have now 2 convolutional layers that keep the same, or increase the number of nodes in the intermediate dense layers and have larger kernels and so on. Maybe also play with the other parameters. The key part is that we stick to the input dimension 28 by 28 by 1, because this is how the images are defined. And we have 10 output nodes, 1 for each digit that we want to classify. And you can see that quite quickly the number of parameters goes up. We can train such a model